So now we're interested in the gradient change. So what we have here is from this point x1 down to this point here, which is our x3, we're going to have a piece of rope which is hanging here. So I haven't drawn it in because it just clutters up the diagram, but we're going to have a piece of rope here that goes through this point here, it goes through this point here, and it goes through this point here. So it's just hanging there. Now what we've done is we've linearized this piece of rope. So really what we'll say is that if we take a point x1 and a point halfway along x2 and a point along x3, we can say this distance here is delta x, this distance here is delta x, and let's say the initial point of the rope here, which is this point, we'll call it delta y1. Now we linearize the rope by drawing a line from this point to this point and from this point to this point, and we look at the gradient of that line there 1 and the gradient of that line there 2. Now what we're going to do is we'll put our thumb on the rope at this point and we'll pull it down to a new position at this point here. So we'll move it a value of delta y. And then we'll look at what happens to the gradients. So we can see the gradient of this line here. So we're linearizing the rope again at the new point, and you can see the gradient has increased at this side, and you can see the gradient has decreased at this side. And we're interested in the change in these gradients 1 and 2 whenever you move this point here to here, and they changed from 3 to 4. So let's just go out and we'll work out what the gradients are at 1, 2, 3 and 4. So we could say the gradient at 1 there, well it's just going to be the rise upon the run. So the rise here is just this value delta y1 and the run is just delta x. So the gradient of the rope, and if we define it at this point here, so the gradient of the rope x1, so that's just the rate of change of the function, that's y derived of x, at x1 is just equal to our delta y1 upon our delta x. So there shouldn't be anything amazing in that. We're just saying that the gradient of this rope is that length divided by that length. And the gradient again can be written as the derivative of the function. So that's just the derivative of the function here at x1. In this case the function is just a straight line. So we could do the same at this side here. We can say that we're just going to have the gradient of this rope is this height here, which we'll call delta y2, divided by this length here, which is our delta x. And again that's just the gradient here, which is the rate of change of the function, but it's the rate of change of the function defined at this point here, x2. So it's from this point here. Of course, because it's linearized, we could have defined at any point along this length and any point along that length, but in order to make the maths work out, we'll just define it at that point and at that point. Now we're also interested in the gradient here at 3 and at 4. So the gradient here at 3, you can see, well, the run's still going to be the same, it's still going to be this value of our delta x, but the height here is changed. The height is now our delta y1 plus the variation, that is the change that we add in, delta y. So we can see here that the gradient of our rope now is delta y1 plus delta y all upon delta x, and that's the gradient y derived of x at x1. Okay, so now we can also look at the value 4, and we can say again the run here is still the same, it's just our delta x, and the rise now, well, it's this little height here. Okay, so this little height here is just going to be given by our delta y2 minus the value of delta y, and that just gives us this little height. So we can say then that our delta y2 minus delta y upon delta x is equal to this new gradient 4. So I suggest if you don't follow that, just take your time and read through it and convince yourself that these are in fact correct. So let's go ahead and we'll see what we can do with these 4 gradients. So we're looking at the change in the gradients. So by the change in gradients, we're looking at the difference in the gradients. So we're going to take gradient 1 away from 3 and 2 away from 4. So when we do that, it's going to give us our delta y upon delta x and minus delta y upon delta x. So we can see that from above here. So we're going to take 1 away from 3. So the delta y, we've taken away that delta y, that disappeared, we'd end up with that delta y upon delta x. And similarly, you can do the same for 4 minus 2. So we're just looking at the change in the gradients whenever we move from this point to that point. Now, we're also going to do the same as we did in the previous video. We knew that a change in position was going to be given by partial f by partial y at a value of x times delta y. But we're not interested in a change of the function due to a change in position. We're interested in the change of a function due to a change in the gradient, which is a rate of change of position. So the rate of change of the position, which is the gradient, is going to be given by our y derivative, not the value of y. So we can get this change here, the delta S2, is going to be partial f by partial y derivative at x1 times delta y derivative. Now it's a bit of a mouthful that, so you take your time and convince yourself of that. If you're unsure, go on to the previous video and you'll see that all we've done here is just replace the position delta y with the gradient y derivative. Now you can do the same for the point x2. We're going to have a partial f by partial y derivative at x2 times delta y derivative. Now what we're going to do is we can replace this delta y derivative at x1 with our value delta y upon x1, and we can replace the delta y derivative at the x2 with our value delta y upon delta minus delta y upon delta x. And I've done that here, so I've just replaced these two terms here with the terms above. So we've got delta S2 is partial f by partial y derivative at x1 times delta y upon delta x minus partial f by partial y derivative at x2 times delta y upon delta x. Now what we're going to do is we'll take out that common factor here of our delta y upon delta x, and we'll also redo this and we'll put the x2 at the left hand side, and we'll be left with minus, and we'll open up the bracket and we'll have all this term in here. So just convince yourself when you multiply that out, you get the minus times minus will give you the plus x1, and you'll be left with the minus x2 there. Now we're doing this because we want to put it into the format of a derivative. Now derivative, the general form of it can be written as f of x plus delta x minus f of x all upon delta x, and its the limit as delta x tends towards 0. And that's roughly what we've got here. We've got something here minus another thing here divided by our delta x. We do have an extra term delta y in there, but we'll just leave that till the end. But we also know here that our value here of x2 is nothing other than x1 plus delta x. So if we see that up here, our x2 is nothing other than x1 plus the delta x. So that means we can replace our value here of our x2 with x1 plus delta x. So we're left with this term here. Now this term here, if we look at it, is nothing other than the quotient for a differentiation, and if we can take the limit as our delta x tends towards 0 of all of this, then what we're going to be left with is, well, it's going to be the value of the minus sign, and it's going to be the normal differentiation, which is d by dx, but we're differentiating the partial f by partial y derivative. So we're left with minus d by dx of partial f by partial y derivative times our delta y. So the change in our function due to a change in gradient is given by minus d by dx partial f by partial y derivative times delta y. So you can see here that what we have is a gradient change, but the gradient change changes in a particular manner. It increases at one side and decreases at another. So the gradient change, it changes over a small infinitesimal distance dx. So that infinitesimal change over that distance is going to be given by our d by dx of that particular change, partial f by partial y derivative. Now again, a little bit of a mouthful, and what we'll do is we'll take this delta 2 and we'll add it on to this is the gradient change and we'll add it onto the position change, and we'll go and get our Euler Lagrange equation. So let's go ahead and we'll do that just now. So finally, let's finish off by deriving the Euler Lagrange equation. Now, we've seen that we can look at the changes due to a change in position, which is delta S1, and we can look at all the changes due to a change in gradient, which is delta S2. And we know that the delta S1, which is the positional change, is given by partial f by partial y times delta y, and the gradient change is given by minus d by dx partial f by partial y derivative. Now, we know that whenever we set all of these changes back to 0, so when we make this delta S1 plus delta S2 equals 0, we know we're back in the equilibrium position. So in order to get back into the equilibrium position, we're going to take out the common factor delta y here. So when we take out our common factor delta y, we're left with partial f by partial y minus d by dx partial f by partial y derivative. Now, we're going to make that equal to 0. So whenever it equals 0, we're in the equilibrium position. So in order for this thing to equal 0, either this thing has to equal 0, or the thing inside the brackets has to equal 0. Now we know the delta y here doesn't equal 0. It does tend towards 0, but it doesn't equal 0. Because if the delta y equaled 0, then we would already be back in the equilibrium position, and none of the last 10 minutes would have happened. So remember that this delta y here is just the distance that you draw the rope. For example, if we're looking at it in terms of a rope, it's the distance that you were to draw the rope down into a new position. So we know that this delta y doesn't equal 0, so in order for it to be an equilibrium position, the thing that's inside the brackets must equal 0. So the thing that's inside the brackets here is called our Euler Lagrange equation. So the Euler Lagrange equation gives us nothing other than the change in position and a change in gradient, and it sets those equal to 0, which ensures that we're in an equilibrium position. So if this differential equation is satisfied, then we know we're in an equilibrium position, and we know that the certain quantity that needs to be that is an extremum is actually being satisfied. So there's been a lot involved in the derivation here, and if you didn't completely understand it, don't worry, because most people probably don't the first time they see it. What's best done is to comprehend it through examples. So that's what we'll do. We'll go over a few examples of using it, and a lot of the time, a lot of the understanding of it is partly based on familiarity as well. So I hope this was of value to you. I'll get you on the next video. Goodbye.